Okay, what is electronegativity?
An atom's affinity is strong.
An atom's affinity, that's
to gain electrons or lose electrons. 4 electrons.
4 electrons. An atom's affinity, 4 electrons. And what does affinity mean? Attraction. And do you remember how we talked about how if you're more attracted to that shared pair, it means it's not nicely shared, it's unevenly shared, and those electrons will be held closer to that molecule. Do you remember that? This is going to help us answer those two concepts, the Vesper diagram and the electronegativity unfairly shared pair of electrons, are going to help us answer whether the molecule itself is polar or not polar. Okay? So with arrows, which we'll learn how to use, indicate the polarity of each bond. With this funny symbol, which means relatively negative, and that funny symbol, which means relatively positive, indicate the polarity of the molecule. This looks like a little music note, kind of, and it is a lowercase d in the Greek alphabet for delta. So it looks like this, delta, and it means partially, actually, is the official science word for it. So partially negative and partially positive. It is not an ion, so we can't just put negative positive. Okay? It is kind of negative. Right? So it's unevenly shared, not a transfer. Remember learning about that a couple days ago, right? So the electrons aren't completely surrounding this Cl minus like that. That would be negatively charged. Whereas if this was a shared electron, then it's not negatively or positively anymore. However, you should know that that chlorine is going to hog the electrons more, right? And so actually in that lovely pair, those electrons are held far closer to the chlorine, right? And so therefore the chlorine will be kind of negative. And the hydrogen will be kind of positive. Partially positive. Not an ion. This is not H+. Okay? Remember this? And I don't know if it was you or the other class that I was telling, but I did say that it's like you take this dot cross diagram, or structural diagram, it doesn't really matter how you draw it. Right, lone pair, lone, oh dear, oh yikes, what is it doing? Oh, hello. Okay, ignore all that for a second, go back there. Lone pair.
You have to realign it, I think.
This is interesting.
Yeah, you have to.
Oh my lord.
Hey.
Yeah.
Wait, no, it's something to do with my pen. My pen's apparently not happy. Mr. Banker told me about this. Okay, when in doubt, start again.
Yeah, it's fine.
Maybe I'll be less dotty. Okay, and this shared pair is like this. So if that shared pair was perfectly shared in the middle, I would kind of draw it in the middle. And if you imagine this to be like one of those old-fashioned weigh scales, you know, you get into the doctor's office, and you stand there, and the nurse moves this metal bar along the thing to see when it equalizes, and that's your weight. Do you know what I'm talking about? Everybody know? Imagine that these electrons are like that bar that the nurse moves. And so this bar is going to move this way, closer to the chlorine. Well, what happens if this is a scale? It tips. The chlorine would tip down, right? If that was a bar in the middle, it's perfectly balanced, but the bar moves closer to the chlorine tips down, making it negative, making it positive, and this arrow bit that I'm talking about in that question is that arrow bit there. Which way did you slide the bar? And why? That was a Davin kind of squeal. Why did I slide the bar to the right?
It's gaining electron.
Not gaining, but it has a higher affinity for the electrons. And how do you know that?
It has a higher number.
Higher number of electronegativity, which you find on the periodic table, right? So when you look up the periodic table, this is something like 3.2, and this is something like, I don't remember, somebody find it for me, and the difference between 2.2, and therefore chlorine is higher. Looks like my 6-year-old son has done this lesson today. Okay, so the next bit of notes, which hopefully I can go to. Okay, this should be a grabber now. Grabber, grabber. Okay. So, if your molecule is polar, it means that the whole thing tips over. Non-polar means that all of those all of those sliders that you've slid bounce to their out, and overall the whole thing doesn't tip anywhere. These are called vectors. Have you done vectors yet in math or physics? Okay, so these are vectors. Only it's 3-dimensional, so it's a bit hard to kind of get your head around. But, okay, come on, please work today. Okay, so 2 types. Non-polar. These are covalent bonds in which electrons are shared equally between 2 atoms due to the atoms having the same electronegativity. For example, Cl2. Or polar covalent bonds is where the electrons are shared unequally due to a difference in electronegativity. So there's the example there for you of your HCl, and I have just completely broken this pen.
Come on.
It's all good. Okay, so what happens when you have 2 bonds though? In each of these I only had one bond, Cl, Cl, one bond, HCl. The slider on that wouldn't move at all. The slider on this would move closer to the Cl. Non-polar, polar. Okay, everybody happy with that? Okay, but what happens if you have 2 bonds like this? So here I have a V-shaped molecule, like this, right? I look at each bond separately. The H and S. S has a higher electronegativity. Okay? Because it's more non-metal than, it's closer to F than H is. So these electrons will be held closer that way. So the slider would move towards the S. Everybody get that? And on this side, the slider would move closer to the S as well. And if this was a V-shaped teeter-totter, seesaw, whatever you say in this country, can you not see that there's a fat elephant here, a fat elephant here, skinny mouse on this end, skinny mouse on this end, and the entire V-shaped seesaw would tip towards the S. It's heavy on the S side. Does everybody see that? So if these are clouds and you're pushing the density, they are clouds, electron density is a cloud, and you're pushing that cloud density on top of the S is going to have more electronegativeness than the H's. Everybody okay with that? So not only are these bonds polar, I have 2 polar bonds, but this entire molecule will be polar, where the S will be relatively negative and the H's will be relatively positive, both of them down in that region. Or in other words, if this was a seesaw, the S would be tipping towards the ground, and those little nice H's would be way up in the air. Get it? And you need the V-shaped diagram in order to visualize that. Those of you that like to draw it like this, from, Science 10, can you see how they might think that, okay, the slider goes this way, the slider goes this way, and actually there's no tipping. So if it was a linear molecule, it wouldn't be tipped. It wouldn't be polar. But because it's V-shaped, it is polar. So that's how Vesper plays a part in here. Does that make sense? If you had a skinny mouse, and a big fat elephant, well, the elephant wouldn't move and the skinny mouse wouldn't fly upwards. It would still just remain level. If it was a straight line. As soon as you change that seesaw into a V shape, now the mice are flying up and the elephant's sitting down at the bottom. Did you get it? So that's how Vesper plays a part in this, because it'll tell you the polarity of the overall molecule. Okay, so let's see if I click on this, and click on this, and go down. Oh dear. Come on again. And go down. Okay. So So molecular dipoles, the resulting of adding of the two dipoles together, like vector addition, and you end up with the S to be relatively negative, and the region between the H's to be relatively positive. Or sometimes they'll draw it with the delta H on both hydrogens, two of them. Okay? So here we go with CH4 then. So if you have CH4, C double bond C, H, 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 H. What shape is it around the carbons? Trigonal planar. Everybody okay with that? Trigonal planar. So this slider is going to move towards the, on this bond, the carbon. Because carbon has a higher electronegativity than hydrogen. So that slider is going to move this way. This slider is going to move this way. What about this one? This slider is going to move this way. This slider is going to move this way. And I'm not sure what's happened there. And overall, the sliders have all pushed in towards the middle, and nothing's changed. So therefore, this is non-polar. Okay? Okay. We'll practice that tomorrow.
Thanks, Steph.
I don't know, you got it. I'm too weak. I'm a little. Can't carry.